We now discuss the EMF induced in a moving conductor. When a conducting rod moves through a constant magnetic field, an EMF is induced in the rod. This special case of electromagnetic induction arises as a result of the magnetic force that acts on a moving charge, as discussed in the previous chapter. Consider the metal rod of length L shown here, moving to the right. The velocity v of the rod is constant and is perpendicular to a uniform magnetic field B that points into the screen. Each charge q within the rod also moves with the velocity v to the right and experiences a magnetic force of magnitude F equals qvb. By using right-hand rule number 1, it can be seen that the mobile free electrons are driven to the bottom of the rod, leaving behind an equal amount of positive charge at the top. Remember to reverse the direction of the force that right-hand rule number 1 predicts, since the electrons have a negative charge. The positive and negative charges accumulate until the attractive electric force that they exert on each other becomes equal in magnitude to the magnetic force. When the two forces balance, equilibrium is reached and no further charge separation occurs. The separated charges on the ends of the moving conductor give rise to an induced EMF, called a motional EMF, because it originates from the motion of charges through a magnetic field. The EMF exists as long as the rod moves. If the rod is brought to a halt, the magnetic force vanishes, with the result that the attractive electric force reunites the positive and negative charges and the EMF disappears. The EMF of the moving rod is analogous to the EMF between the terminals of a battery. However, the EMF of a battery is produced by chemical reactions, whereas the motional EMF is created by the agent that moves the rod through the magnetic field, which, in this case, was the origin of the pushing force. The fact that the electric and magnetic forces balance at equilibrium can be used to determine the magnitude of the motional EMF. We start by noting that the magnitude of the electric force acting on a positive charge Q at the top of the rod is E times Q, where E is the magnitude of the electric field due to the separated charges. The electric field magnitude is given by the voltage between the ends of the rod, or the EMF in this case, divided by the length L of the rod. Thus, the electric force is QE equals Q times the EMF divided by L. According to equation 21.1, the magnitude of the magnetic force is equal to BQV sine theta, where theta is the angle between the magnetic field and velocity vectors. In our case, theta equals 90 degrees because the charge Q moves perpendicular to the magnetic field, and the sine of 90 degrees is equal to 1. Since these two forces balance, we have Q times the EMF divided by L equals QVB. The Q's cancel, and the EMF is equal to VBL. This is the motional EMF when V, B, and L are all mutually perpendicular. As expected, the EMF equals 0 volts when the velocity equals 0 meters per second because no motional EMF is developed in the stationary rod. Greater speeds and stronger magnetic fields lead to greater EMFs for a given length L. As with batteries, EMF is expressed in volts. Suppose now that the rod is sliding on conducting rails that form a part of a closed circuit, and L is the length of the rod between the rails. Since the moving rod possesses an EMF, it acts like a battery in a complete circuit. Due to the EMF of the rod, electrons flow in a clockwise direction around the circuit. Positive charge would flow in the direction opposite to the electron flow, so the conventional current I flows counterclockwise and lights the light bulb. Our discussion now leads to the relation between motional EMF and electrical energy. Motional EMF arises because a magnetic force acts on the charges in a conductor that is moving through a magnetic field. Whenever this EMF causes a current, a second magnetic force enters the picture. The second force arises because the current I in the rod flows in a direction that is perpendicular to the magnetic field. The current, and hence the rod, experiences a magnetic force whose magnitude is given by equation 21.3 as F equals ILB sine theta, and is equal to ILB since theta equals 90 degrees. The direction of this force is specified by the right-hand rule and is opposite to the velocity v of the rod, and thus points to the left. By itself, this opposing force would slow down the rod, and here lies the crux of the matter. To keep the rod moving to the right with a constant velocity, a counterbalancing force must be applied to the rod by an external agent, such as the force provided by the hand, or F hand, as shown here. The counterbalancing force, F hand, must have a magnitude of ILB and must be directed opposite to the magnetic force. If the counterbalancing force were removed, the rod would decelerate under the influence of the magnetic force and eventually come to rest. During the deceleration, the motional EMF would decrease and the light bulb would eventually go out. We can now answer an important question. Who or what provides the electrical energy that illuminates the light bulb? The provider is the external agent that applies the counterbalancing force, F hand, needed to keep the rod moving. This agent does work, and the amount of work is W equals F hand times X, where X is the displacement of the rod. This work is equal to the electrical energy used to illuminate the light bulb.